If our universe is truly rotating inside a colossal black hole, would you believe it? Across the vast hush of space, where ancient light travels for billions of years to reach us, James Webb has revealed something that shakes the foundations of what we think we know. Galaxies so distant they feel like whispers from creation itself suddenly blaze like sparks guarding the first stories of the cosmos. This video offers astonishment, the value of new understanding, and a gentle drift into mysteries yet untouched. Share your thoughts. What do you believe hides behind those distant lights? And now, what exactly are the ultra-bright, ultra-distant objects JWST has found beneath the quiet shimmer of the early cosmos, where light must struggle across billions of years to reach our waiting eyes? The James Webb Space Telescope has uncovered a collection of objects so luminous, so distant, that they seem almost impossible. Astronomers expected the dawn of the universe to glow softly like embers just beginning to form. Yet what Webb revealed was more like a scatter of bright lanterns hung against the very edge of time. 300 of them, gleaming far brighter than the laws of cosmic evolution would normally allow. Scientists call them candidate galaxies because they may represent systems born when the universe was barely a few 100 million years old, a moment when matter was still uncertain, when stars were only beginning to ignite their first fires. To name them candidates is a humble gesture, a recognition that we are standing before something that appears to be a galaxy, yet behaves like nothing we have ever modeled. As astrophysicist Garth Illingworth once said, "Every time we push our instruments to see earlier, the universe answers with something stranger than the last surprise." And the strangeness here is unmistakable, as if creation itself has left a few bright fingerprints on the outer walls of our understanding. These luminous objects rise in defiance of the standard model of cosmology, a framework that has served us faithfully for decades, a framework that told us galaxies should grow slowly at first, timidly, gathering their stars grain by grain. But Webb's discoveries do not whisper, they blaze. Some of these candidates shine with the intensity of galaxies that should be billions of years old, yet they appear in an era when the cosmos was still a child learning how to breathe. Astrophysicist Priyamvada Natarajan once reflected, "If something forms too early, too fast, it forces us to revisit the cosmic script we thought was already written." It is that revision that now sits quietly on every astronomer's desk, waiting. What makes these objects more fascinating is the dropout technique used to identify them, a method that searches for signatures slipping into redder light while vanishing in the blue, as though they are disappearing backward into history itself. This technique is like listening for what is no longer audible, seeing what is no longer visible, trusting the faintest of cosmic footprints left on the waves of stretched light. Yet even after detecting them, the question remains, are these truly ancient galaxies? Or are we misreading a kind of cosmic mirage? Spectroscopy will answer this, splitting their light like a prism cracking a forgotten secret into its colored truths. It is an instrument that speaks the language of atoms, a quiet interpreter of distance and age. And when it finally tells us what these objects are, the universe will either confirm our boldest theories or undo them with a single whisper. As the conversation continues, one truth emerges, gently yet firmly. If even a handful of these objects are real galaxies formed at such early times, then the cosmos grew up far quicker than we imagined. like a child who learns to speak before it learns to crawl. It would mean that star formation, chemical enrichment, and galactic assembly were all unfolding at a speed that borders on the miraculous. In the words of Nobel laureate Adam Rees, the universe has never been shy about reminding us how little we truly understand. There is a gentle irony in this discovery, a softness almost poetic. We invent models to tame the stars, to arrange them into neat timelines and predictable behaviors. Yet the stars obey no timetable, no model. They rise from chaos, burn through epochs, collapse and sing again. And these early luminous objects are simply another verse in that cosmic hymn, reminding us that science is not a cage but a lantern. As Webb peers deeper, the line between what we know and what we assume thins like the surface of a bubble stretching in sunlight. Perhaps these galaxies reveal parts of the universe that evolved unnaturally quickly. Or perhaps more daring still, they hint that our understanding of the early cosmos has been incomplete from the very beginning. My own reflection drifts somewhere between awe and humility. For these objects speak a language older than our species, older than our sun. They remind me that certainty is the slowest enemy of discovery. That curiosity is the only compass worth carrying when we step into the dark. If the universe is bolder than our equations, then perhaps we too must be bolder in how we listen to it. There is a quiet lesson hidden in their distant glow, a lesson about patience and wonder, and the courage to let go of what we think is final. We are not here to force the cosmos into our understanding. We are here to let the cosmos expand our understanding. And as you journey with me through these mysteries, if this gentle voyage into the edge of time makes your heart stir or your curiosity spark, let that feeling guide you to support the channel. A quiet like, a thoughtful subscription, so that more stories like this may continue to drift toward you. The universe is wide, but wonder becomes wider when shared. In the end, these luminous points are more than scientific anomalies. They are reminders that the cosmos still keeps its secrets close, offering them not to those who demand, but to those who listen. Perhaps that is the hidden gift they carry, a reminder that even at the dawn of existence, light found a way to bloom, to speak, to endure. And now, as we turn gently to the next question, let us breathe with the same patience as the stars. What exactly did Webb see in those distant fires? And why do these strange galaxies refuse to fit the universe we thought we understood? The early universe was supposed to be simple, quiet, and almost childlike in its cosmic infancy. According to the standard cosmological model, those first few 100 million years should have been a time when only the earliest stars flickered awake. Small clusters of light wrapped in vast oceans of dark matter. Nothing more. Galaxies, as we understand them, should not have existed yet. But JWST has a way of whispering truths that break our comfortable assumptions. And in the soft, crimson glow of the universe's distant past, it has revealed fully formed galaxies shining where only lonely stars were meant to be. This is why their existence feels so profoundly unusual, so unexpectedly disobedient to the rules we thought the cosmos followed. Galaxies require time. Time to gather mass. Time to ignite generations of stars. Time to build the heavy elements that shape worlds and breathe life into cosmic chemistry. Yet here they were, gleaming like lanterns floating on a primordial river, already bright, already complex, already ancient in a moment that should have been too young to carry such grandeur. As astrophysicist Priyamvada Natarajan once said, "The universe is always more imaginative than we are." Her words feel like a sigh drifting through these discoveries, because each strange galaxy reminds us that creation does not always grow in linear steps. Sometimes it leaps. To identify these rebellious structures in the deep night, researchers turn to a method as subtle and elegant as a painter, searching for the faintest shift of color on a canvas. The dropout technique, though technical by name, is essentially a meditation on vanished light. High redshift galaxies are so distant that their ancient photons have been stretched by expanding space until the wavelengths slip into redder and redder tones. So red that they disappear from blue filters entirely. In images taken across multiple wavelengths, they appear present in the red, but missing in the blue. They drop out, like a ghost vanishing from one room only, to reappear quietly in the next. By tracking that disappearance, astronomers can estimate how far back in time the light originates, inferring redshifts so high that the galaxies become windows into an era when the cosmic dawn was barely beginning to glow. This method is vital for detecting early galaxies because at such distances almost all visible light is erased or stretched beyond recognition, leaving infrared as the only surviving messenger. JWST, tuned perfectly to the faint warmth of ancient starlight, becomes a kind of archivist of the universe's most fragile memories. It listens for what has been lost, not just what shines. And in that quiet listening, the dropout technique becomes the key that unlocks galaxies that should never have been able to exist. One by one, these candidates emerged in JWST surveys. Small but blazing, young but impossibly evolved. They offered more than anomalies. They offered puzzles about the nature of cosmic time itself. How could stars have lived and died so quickly to enrich these systems with heavy elements? How could gravitational structures assemble with such speed when theory predicts slow growth across hundreds of millions of years? It is as though the early universe breathed faster, pulsed harder, and formed stars in a furious whisper that we never expected to hear. Astrophysicist Avi Loeb once remarked, "When data disagrees with theory, it is the theory that must adapt." His statement resonates deeply here because these galaxies are not errors. They are messages. So many of them have appeared that the pattern can no longer be ignored. There is something in the early cosmos we have not yet understood. As we contemplate this mystery, a gentle thread connects each part of the story. The strange galaxies, the vanished wavelengths, the stretched light, the improbable chemical richness. They all invite the same quiet realization that the universe grows in ways we are still too young to grasp. To imagine the early cosmos, picture a night as deep as eternity. And in that night, small pockets of light bloom far sooner than should be possible. The darkness around them remains vast, unbroken, ancient. But within that vastness, stars ignite in clusters dense enough to rival modern galactic cores. This density may explain the rapid enrichment of elements, but it also raises more questions than it settles. As cosmologist Wendy Friedman once said, "Every measurement is a confrontation with the unknown." Her voice echoes softly through these discoveries as JWST confronts the unknown not with noise, but with silence, patient persistence, and the gentle accumulation of ancient light. The galaxies we find challenge the narrative of a slow, methodical cosmic build-up, suggesting instead a universe whose earliest moments were intense, vibrant, and wildly creative. Perhaps the birth of stars was not a quiet dawn but a storm of formation, a cosmic rain of light cascading faster than our theories dared to imagine. The dropout technique guides us through this storm like a compass pointing toward vanished photons, helping us wander through epochs where no human eye could ever survive. It teaches us to follow absence as much as presence, to see meaning not only in what appears, but in what disappears. In the drifting rhythm of the cosmos, these early galaxies become reminders that the universe is not bound by our expectations. It moves with its own breath, its own timing, its own ancient heartbeat. And as JWST peers deeper, each discovery feels like the soft turning of a page in a book far older than memory, far wiser than mathematics. A scientist once said, "We are not studying the universe. We are listening to it." And in this gentle listening, these early galaxies sing a song that rewrites the opening verses of cosmic history. Their existence is not merely unexpected, it is transformative. They ask us to loosen our grip on old assumptions, to breathe with the universe rather than constrain it, to let theory flow like starlight rather than crystallize like stone. As the narrative drifts toward its quiet end, we are left with a sensation not of confusion but of wonder. The early universe, once imagined as a dim and silent nursery, now reveals itself as a place of fierce brilliance, a realm where galaxies rise earlier than dawn. And through the dropout technique, we learn that even the faintest disappearance can be a doorway, a whisper, a path back to the beginning. In this serene cosmic meditation, we are reminded that science is not the opposite of poetry. It is simply poetry written in the language of truth. And as we drift deeper into the mysteries uncovered by JWST, one question glows softly ahead. What else is waiting to be found in the light that has traveled so far to reach us, beneath the velvet dark of the early universe, where light stretches thin like a final breath across cosmic time? A quiet question lingers in the minds of astronomers who study these impossibly bright, impossibly distant objects now emerging in the images of James Webb. Are they truly as far away as they seem? Or are our senses being fooled by some ancient trick of light itself? The universe has always been a patient teacher, offering clues only to those willing to listen deeply. And yet even the most seasoned scientists admit that these new lights challenge the very rhythm of our understanding. As astrophysicist Garth Illingworth once said, "The early universe refuses to behave the way we expect it to." When we look at these bright points scattered against the black, we must first ask whether they stand at the true edge of time, or whether we are witnessing something closer, masquerading as a galaxy from the dawn of creation. In astronomy, distance is a fragile illusion, a relationship between light, expansion, and our own assumptions about how galaxies should glow as they evolve. Some scientists whisper that these lights could be imposters, ancient quasars, adorned in the wrong spectral clothing, or compact star clusters whose brilliance momentarily rivals entire galaxies. Others imagine dusty newborn galaxies where the first generations of stars ignite so furiously that they outshine their size and age. But speculation without measurement drifts like smoke across the cosmic sea. And so we turn to the one instrument capable of stripping illusion from truth: spectroscopy. Spectroscopy is the universe's fingerprint, a subtle unraveling of light into its quiet components, revealing what distance hides and what brightness alone cannot tell us. As Nobel laureate Subramanian Chandrasekhar wrote, "The universe is not only stranger than we imagine, it is stranger than we can imagine." And spectroscopy is the tool that allows us to step just a little farther into that strangeness. Only through this prism-like examination do we learn whether these objects truly sit 13 or 14 billion light-years away, whether their redshift is honest, whether their light began its journey when the universe was barely stirring from darkness. Without spectroscopy, we are staring through frosted glass, catching only shadows of the entities beyond. And yet, suppose spectroscopy confirms the most daring possibility, that these are indeed galaxies from the first few 100 million years of cosmic history. If so, our textbooks tremble a little, and our theories begin to loosen around the edges. For galaxies, this early should be faint, small, chemically simple. They should be childhood sketches compared to the enormous systems we see today. But instead, some shine fiercely, boasting complex chemistry, the signatures of generations of stars already born, lived, and died. This violates the carefully drawn timelines in cosmological models, the ones predicting slow growth, gentle accumulation of mass, delayed enrichment of elements heavier than helium. If these galaxies are real, then the universe grew up faster than we ever imagined. As cosmologist Priyamvada Natarajan has said, the early cosmos was a far more dynamic workshop than our theories allowed. And here the story turns softer, more contemplative, because science does not break when theories fail. It breathes, expands, and adapts like a living organism, adjusting to new light. If these bright objects force us to redraw the map of cosmic dawn, then that redrawing is not a defeat. But a deepening is less than span, is greater than a widening of the path toward truth. But there is another possibility, quiet yet profound. What if these are not galaxies at all, but a new category of cosmic phenomena emerging from the fog of the early universe? Perhaps dense star clusters blazing with supermassive stars, or black hole accretion disks that formed far earlier than predicted. Perhaps something no theory has yet dared to propose, born in conditions we cannot recreate, carrying the handwriting of physics still hidden from us. The universe is under no obligation to be simple, nor to fit the diagrams we draw on paper. Neil deGrasse Tyson once remarked, "When the universe surprises us, it's a reminder that we are only beginning to learn the alphabet of reality." And these objects, whether galaxies or something more elusive, are letters in that ancient alphabet, glowing across time. As we drift deeper into the mystery, we notice how each discovery softens the boundary between what we know and what we hope to know. If they are true galaxies, the cosmic timeline must be rewritten, If they are not, then the universe has introduced a new actor onto the stage, a phenomenon that shaped the first chapters of existence. Either way, we stand at the edge of revelation, learning once again that knowledge is not a destination, but a journey into a darkness that becomes less frightening each time light touches it. So we look and listen and wait for the next whisper carried by photons older than every mountain and ocean and memory we know. The universe speaks slowly, and our task, as always, is to stay awake long enough to hear what it is trying to say. The ancient light that reaches us today began its journey long before Earth had oceans, before sunlight ever touched the skin of any living creature. It drifts across the void like a quiet memory, a whisper from the dawn of all things. And as we follow that fading glow with our most powerful instruments, we discover that the universe remembers far more than we ever imagined. For decades, the Hubble Space Telescope was our lantern in the dark. When it detected GNZ 11, astronomers called it a miracle in the deep field. Its redshift was so large that it felt like Hubble had stretched a hand backward through nearly all of cosmic time, catching the glimmer of a galaxy born just a few 100 million years after the Big Bang. As astrophysicist Garth Illingworth once said, "Every time we think we've reached the edge of the observable universe, the universe moves the edge farther away." But then came the James Webb Space Telescope, a machine built not just to see farther, but to remember deeper. With its enormous mirror sliding open like a golden eyelid in the cold of space, JWST began to gather infrared light so ancient that it barely existed as a wavelength anymore. And in that fragile light, it shattered record after record. The discovery of Jade's GZ14 felt like the cosmos stepping closer to us, revealing a shape behind the curtain we thought would never lift. Its redshift pushed us to the very brink of what telescopes can measure, showing a galaxy forming in a universe still trembling from its own birth. Astronomer Emma Curtis Lake described this moment simply: "We are seeing the universe when it could barely form stars, and yet it is already building galaxies." But the true shock came later, in the form of a tiny glowing ember named MOMZ14. A galaxy so strange, so defiant of expectation, that many scientists reread the data in disbelief. MOMZ14 is small, barely 500 light-years across. In the cosmic scale, it is the size of a quiet town in the middle of a great continent. Too small to carry the weight of history, too young to shape anything but the first flickers of light. And yet, it shines with the brilliance of tens of millions of newborn stars. Its light is sharp, bright, unreasonably fierce for something so early in cosmic time. What unsettled astronomers even more was what they didn't find. In galaxies with such intense star formation, there is almost always a supermassive black hole anchoring the center, shaping the gravity, feeding the internal storms. Yet, MOMZ14 seemed empty at its heart, lacking the dark engine we expect in every thriving young galaxy. "It is like seeing a city without a power grid," one researcher remarked. And yet, all the lights are still on. Then came the nitrogen. When JWST dissected the galaxy's light through spectroscopy, it revealed an abundance of nitrogen far beyond what theory predicts for the early universe. Nitrogen is not the signature of first-generation stars, but of stars that have already lived, already died, and enriched the clouds that follow them. This means that before MOMZ-14 formed, there must have been earlier generations of stars, rising and collapsing in cycles that should not have existed so soon after the Big Bang. The universe this young should have been simple, quiet, chemically untouched. Yet here was a galaxy behaving like a seasoned storyteller, carrying memories from a past that should not logically exist. The contradiction is profound. If MOMZ-14 is real as we observe it, then the early cosmos was not a slow unfolding dawn, but a rapid blaze of creation. Galaxies formed faster, stars lived and died sooner, and chemical complexity blossomed in an era where physics tells us it should not yet have bloomed. The early universe is proving to be impatient. Astrophysicist Priyamvada Natarajan once said, "It wants to grow up faster than our models allow." The discovery forces us to ask quietly uncomfortable questions. Did the first galaxies form in bursts more violent and frequent than we imagined, reshaping the cosmic landscape with an urgency we have underestimated? Did dark matter halos gather more quickly than predicted, cradling star factories that ignited almost instantly? Did the earliest stars live short, furious lives, filling the young universe with metals and memories far ahead of schedule? Or perhaps the universe itself behaves differently at its beginning, governed by rules that soften with age like the fading rigidity of an old tree. As we drift deeper into the insight that Webb provides, we begin to see the early universe not as a cold mathematical structure, but as something almost alive. A vast cosmic tide rising and collapsing in rhythms we are only beginning to hear. The light from MOMZ-14 is not just data. It is a message. A reminder that the universe is older in spirit than in years, wiser than its timeline suggests. And as we let that light settle into our understanding, we sense the quiet truth at the heart of cosmology. That the farther we look, the more the cosmos reveals not answers, but questions dressed in starlight. If a tiny galaxy in the first breaths of time can be complex, enriched, and vibrant, then what else waits behind the next veil Webb lifts? What stories were written in the fires of those early stars? And what chapters have we not yet learned to read? And so we continue drifting through this cosmic meditation, letting science turn gently into poetry, letting the quiet glow of ancient galaxies soften the distance between wonder and understanding. The universe is speaking in the only language it knows, light traveling endlessly across the dark. And the question remains, if MOMZ-14 can exist so early, so bright, so impossibly enriched, what else is waiting to rewrite our idea of the beginning? When we gaze into the first light of the universe, carried to us on waves that have crossed billions of years of silence, there is a moment when reality seems to soften, when the boundary between what we know and what we only dare to imagine begins to dissolve. That moment has arrived again with the discovery of the ancient galaxies we now call the little red dots. Tiny in appearance, yet impossibly bright. Glowing like embers kept alive by some cosmic breath that refuses to fade. And they are far more numerous than any model ever predicted. At first, astronomers believed these flickers were rare exceptions, brief curiosities, isolated outliers in the long unfolding of cosmic history. Yet James Webb has revealed an unexpected abundance, a quiet crowd of ancient structures forming far earlier than we believed possible. As astrophysicist Priya Natarajan once said, "When the universe contradicts your expectations, that is not a failure of theory. It is the universe inviting you to think deeper." So we think deeper. And the deeper we go, the stranger the story becomes. These little red dots appear at times when galaxies were not supposed to exist in such maturity, at epochs when matter should still have been drifting toward its future forms, like clay not yet molded by cosmic hands. Yet here they stand, luminous, compact, dense, as though the universe in its childhood hurried forward with extraordinary purpose. Why are they so many? And why do they shine so fiercely? Observations tell us that these galaxies form stars with astonishing speed, burning through their gas supplies as if racing against some unseen clock. The early universe, instead of being a calm nursery, seems almost wild, a realm of intensity, a cosmic storm where matter rushed together in ways our equations never anticipated. As cosmologist Brian Keating remarked, "Discovery is an assault on certainty, and certainty rarely survives the first contact with new light." This new light forces us to confront a possibility that feels both thrilling and unsettling, that we may be missing something fundamental about the dawn of galaxies. Something in our theories is too slow, too gentle, too orderly to match the feverish dance that JWST shows us. Perhaps the building blocks of matter clustered faster. Perhaps dark matter behaved differently. Perhaps cosmic inflation seeded the universe with regions of higher density than we expected. Or perhaps, in the quiet spaces between prediction and discovery, lies a phenomenon we have not yet named. Then comes the strange and shimmering presence of MOMZ-14, a galaxy so distant the universe was only a toddler when its light began the long journey to our eyes. MOMZ-14 is small, roughly 500 light-years across, but it burns with the brilliance of galaxies many times its size. It forges stars at a rate that defies every expectation, like a forge stoked by unseen winds. And in its chemical signature lies another shock, an unexpected richness of nitrogen, implying that multiple generations of stars had already formed and died before this galaxy released its ancient glow. But how could so many generations pass in such a short cosmic moment? How could a galaxy mature before the universe itself had settled into its early shape? Jocelyn Bell Burnell once said, "Nature is rarely simple, but she is always elegant." MOMZ-14 is that elegance, quiet, luminous, and utterly unwilling to fit inside the tidy lines of our cosmological sketches. Its very existence pushes us toward the edges of our understanding. And there, standing with us in this dim frontier, are the little red dots, filling the darkness like notes of a forgotten cosmic song. The questions unfold slowly, like petals opening in a cold dawn. What force brought matter together so quickly? Why is star formation so intense? Why do these galaxies appear so red, so dense, so alive within moments of cosmic birth? Even more bewildering, some of these galaxies appear to lack supermassive black holes. structures we believed were essential for shaping and regulating early galaxies. Without these gravitational anchors, how do they grow? How do they sustain their luminous frenzy? The standard models simply whisper, unable to speak up against the evidence before them. Perhaps dark matter collapsed differently. Perhaps the rules governing early star formation contain hidden clauses we have yet to read. Or perhaps the universe in its first breaths was not governed by the same quiet order we see today. MOM-Z14 becomes a symbol of this mystery. A soft red thorn in the side of our models. It is the galaxy that should not be. And yet there it glows. Patient, ancient, and unbothered by our confusion. As Nobel laureate John Mather once reflected about such paradoxes, the universe is not obligated to make sense to us. But it often leaves clues if we listen closely. And so we listen. Through the quiet hum of data. Through spectra that stretch like rainbows across the void. Through images where every faint pixel holds the weight of billions of years. The more we listen, the more a pattern begins to emerge. The early universe might have been denser, more turbulent, more efficient at sculpting matter into structure. Star clusters may have merged rapidly, feeding on dense pockets of gas seeded shortly after the Big Bang. Perhaps the timeline between primordial plasma and mature galaxies is not a long, steady river, but a rapid cascade, a sequence of cosmic waterfalls. And in these waterfalls, the little red dots are droplets frozen in light. They tell us the universe did not walk into its early years. It sprinted, burned, roared with creativity. This early fury has been invisible to us until now because our instruments were too weak to see it. Our theories too narrow to expect it. What are we missing? Perhaps the laws of physics remain the same, but their earliest expressions were far more extreme. Perhaps dark matter halos formed faster, collapsing like snowdrifts under their own weight, creating pockets where galaxies ignited in violent bursts. Or maybe we are glimpsing the legacy of quantum fluctuations, magnified during inflation, forming regions of exceptional density where galaxies could flourish long before the cosmic web finished weaving itself. As theoretical physicist Ethan Siegel often reminds us, every breakthrough begins as an inconsistency. And here, with MOM-Z14 and its kin, the inconsistencies glow brightly against the deep canvas of space. These discoveries do not destroy our models. They enrich them. They reveal which threads need reforging. Our theories are not wrong. They are simply incomplete. To complete them, we must ask new questions. We must reshape our expectations. We must allow the universe to guide us gently toward a more intricate truth. And as we settle into this thought, floating in the slow current of cosmic reflection, a deeper understanding begins to unfold. The early universe was not a quiet cradle, but a restless dreamer, forming galaxies with a passion that challenges our imagination. These little red dots are its whispers, its memories, its first fiery sketches of structure, and MOM-Z14 stands at the center of this revelation, a reminder that the cosmos does not move according to our comfort, but according to its own mysterious rhythm. So we breathe with that rhythm, letting the questions settle like dust on a quiet windowsill. And in the stillness we ask again, if so many ancient galaxies shine where we least expect them, what else lies waiting just beyond the threshold of our instruments? Our theories, our imagination. And in that question, whispered softly across the stars, begins the next chapter of discovery. The deeper we look into the cosmos, the more it feels as though the universe is quietly rewriting itself beneath our gaze. And now, with the next generation of telescopes preparing to open their mirrors toward the ancient dark, we find ourselves standing on the threshold of revelations that might reshape everything we believe about cosmic origins. The James Webb Space Telescope has already peeled back veils we once thought permanent, revealing infant galaxies glowing fiercely when the universe was barely awakening. But soon, another instrument will join this silent symphony of light, the Nancy Grace Roman Space Telescope. A machine designed not just to see deeper, but to see wider, to gather the sky the way an ocean gathers waves. Astronomers call it a game changer, not because it will replace Webb, but because it will amplify it. Roman's wide field will be able to scan vast stretches of the early universe, mapping structures so ancient that their light began its journey long before our planet had even solidified. Where Webb can study a square of sky the size of a grain of sand held at arm's length, Roman will survey an expanse hundreds of times larger, capturing thousands of early galaxies in a single frame. It is in this union of depth and breadth that we will discover whether the early cosmos was truly as crowded as Webb now hints. When JWST first revealed luminous galaxies burning fiercely just a few 100 million years after the Big Bang, many scientists felt a shiver of disbelief. These objects were supposed to be rare, tiny, still forming their first primitive stars. But instead, we found cosmic cities glowing as though countless generations of stars had already lived and died. The Roman telescope will allow us to understand whether these early overachievers are isolated wonders, or merely the first whispers of a universe far more dynamic and fertile in its youth than we ever imagined. As cosmologist Brant Robertson once said, "Every time we widen our field of view, the universe shows us it has been busy in ways we didn't predict." If Roman finds hundreds, or thousands, of these bright young galaxies, then our theories will need to bend, soften, or perhaps give way completely. Because such abundance would imply that structure formation began almost instantly after the cosmic dawn, as though the universe knew what it wanted to become. It is a haunting idea, almost poetic, that the cosmos may have assembled itself with a quiet urgency, shaping stars and galaxies long before physics says it should have. And when science encounters urgency where there should be none, we sense the presence of a deeper layer waiting to be uncovered. That is where the boldest hypotheses begin to surface, rising gently like bubbles from the floor of a deep ocean. Among them, one idea stands out not for its simplicity but for its audacity. The suggestion that our entire universe may exist inside a black hole. Though it sounds like the premise of a myth or a dream, several physicists have explored this possibility with quiet seriousness. The reasoning begins with symmetry, with pattern, with the haunting similarity between the Big Bang and the formation of a black hole. In both cases, immense amounts of matter collapse into a state of extreme density, forming a boundary known as an event horizon. Inside that boundary, space and time behave in ways that defy intuition. As theoretical physicist Lee Smolin once said, perhaps black holes are the wombs of new universes, not the tombs we once believed them to be. If a collapsing star in some parent universe were dense enough, it could form not a simple singularity, but a rebounding core, a region where torsion and quantum forces generate a counterpressure, preventing infinite collapse and allowing a new expansion to bloom inside. This expansion could be what we perceive as our universe. The Big Bang, not as an explosion from nothing, but as a quiet recoil from a previous cosmic structure. The concept is called black hole cosmology, and although still speculative, it offers a framework that unites ideas once thought incompatible. It enriches the universe with lineage, with ancestry, with the possibility that every black hole we observe in our night sky might be the seed of another cosmos. The notion echoes the words of physicist Nikodem Popowski, who proposed, "We may be living inside a black hole that exists in another universe." These ideas gain weight when we encounter the peculiar behavior of galaxies across the sky, many of which seem to rotate in the same direction. In a universe that should be random on large scales, this gentle alignment is surprising. It whispers of an imprint, a preferred direction, a memory left over from a larger structure in which our universe might once have been embedded. Could it be the rotational signature of a parent black hole, carried forward into the newborn universe it created? Even if that idea proves wrong, the mystery remains compelling, tugging softly at our curiosity the way tides pull gently at the shore. Some astrophysicists caution that perhaps the anomaly lies not in the cosmos but in our measurements, especially those concerning the rotation of our own Milky Way. If our galactic motion has been slightly miscalculated, the patterns we see across the sky might shift back into familiar randomness. Yet even the most cautious voices admit that the data leaves room for wonder, room for the unexpected. And in science, such room is often where breakthroughs germinate. As we drift through these possibilities, it becomes clear that telescopes like Roman are not merely instruments. They are extensions of human longing. Every mirror polished, every detector cooled, every photon gathered from the farthest reaches of spacetime is an act of hope, a gesture of curiosity woven through generations. What Roman will reveal is not yet known, but it will likely provide the statistics we need to test these bold questions. If early galaxies are abundant, if they cluster in unexpected ways, if they exhibit properties that align with predictions of black hole cosmology, then the idea that we inhabit the interior of a larger structure will move from speculation to something more tangible. In this moment, as we anticipate these discoveries, the universe feels almost alive. Not in a literal sense, but in the way it responds to our search, revealing secrets only when we are ready to perceive them. When Karl Schwarzschild first formulated the mathematics of black holes during wartime, he wrote, "This solution shows something profound, something far beyond our senses." More than a century later, that sense of the profound remains, wrapping around us like the soft dark of a cosmic evening. The Roman telescope's mission will not only deepen our understanding of cosmic evolution, it will help us discern the hidden architecture of reality itself. Whether we find that the universe behaves like a child of a black hole, or whether we uncover a new principle entirely, the journey promises to be one of the most poetic endeavors in scientific history. For in searching outward, we also search inward, toward the quiet core of our own desire to understand. As we imagine Roman sailing through space, its instruments waiting to drink the ancient light, we find ourselves suspended in a moment of anticipation. The future of cosmology feels like a held breath, a subtle pause before revelation. And within that breath, we sense a truth Carl Sagan once captured with gentle clarity. Somewhere, something incredible is waiting to be known. Whatever we discover, the universe will remain vast, mysterious, shimmering with questions that drift just beyond our reach. But with each new telescope, each new lens pointed into the infinite, we take another small step across that cosmic ocean. And perhaps, as we travel farther, we will learn that the universe is not a cold expanse, but a story still unfolding. A story we are finally learning how to read, across the quiet stretches of the cosmos, where the faint hum of starlight drifts like a memory older than time itself. Astronomers have stumbled upon a pattern that should not exist, a whisper of order woven into what ought to be chaos. Many galaxies, separated by unimaginable distances, seem to spin in the same direction, turning together like a vast cosmic choir following an invisible conductor. In a universe assumed to be random, this gentle synchronicity feels like a soft contradiction. As the astrophysicist Michael Longo once remarked, if the universe prefers one direction over another, then something profound is guiding its shape. The question deepens when you consider the scale. Galaxies born in different epochs, forged in different cosmic weather, still tracing a shared sense of rotation. It is like finding thousands of drifting leaves across an endless lake, all circling the same way, despite no wind to command them. One might expect symmetry, a balance of clockwise and counterclockwise. Yet, the universe offers a subtle hint that the early blueprint of spacetime may have been imprinted with a preferred twist, a primordial swirl. The cosmologist Niayesh Afshordi once said, "The universe may carry memory in its motion." And perhaps this memory is what we are witnessing now, a relic of an origin that was not as neutral as the textbooks suggest. As we drift deeper into this mystery, another question awaits, like a shadow behind the light. What secret could cause such a cosmic preference? Such a gentle bias in spin? Some scientists whisper that this pattern might point beyond the familiar landscape, reaching toward an idea once thought too wild even for theoretical physics. The possibility that our universe itself was born inside the belly of a rotating black hole. To follow that thought is to stand at the threshold of the event horizon, that silent border where no message returns, where light loses its name and time bends into something unrecognizable. What lies inside such a horizon? No one can say with certainty. It is a place where the equations we trust begin to tremble, where geometry becomes fluid, where the familiar collapses into the nameless. The physicist Kip Thorne once admitted, "Inside a black hole, our understanding of reality simply breaks. We can describe the outside perfectly. We can map the boundary. But the interior remains a realm where science stares into silence. It is like pressing your hand against frosted glass, aware that something exists beyond it, but unable to perceive its shape. Why is it unknowable? Because the laws of physics that define our world unravel inside that gravitational abyss. The narratives we tell about time, motion, distance, identity, all lose coherence as space-time twists so violently that even information cannot survive its journey outward. And in this strange empire of gravity, some theories imagine a rebirth rather than a tomb, a bounce instead of a final fall. Here enters the delicate notion of a baby universe, a young cosmos blooming quietly inside a parent black hole, like a seed hidden within a shell, insulated from the outside, yet expanding into an entirely new reality. In Einstein, Cartan theory, torsion, the subtle twist of space-time caused by particle spin, might counteract the collapse at the core, preventing the singularity from forming, allowing instead a rebound, a cosmic exhale that becomes a new universe. The theorist Lee Smolin once beautifully expressed, "Every black hole may be a womb of stars, of galaxies, of life." If this is true, then our universe carries the imprint of the rotation of the black hole that birthed it. The galaxies spinning together like drifting petals might be the echo of that ancestral twist, a faint rhythm passed down through cosmic generations. In this view, the universe is not an isolated miracle but part of an endless tree of creation, each cosmos budding from the collapse of another. The astrophysicist Roger Penrose once said, "Perhaps universes come and go like breaths, and when one listens to the soft turning of the galaxies, it is difficult not to imagine such a poetic cycle unfolding across eternity." As we contemplate this lineage of universes, the boundary of the event horizon starts to feel less like a wall and more like a doorway. The unknown becomes not a void but a cradle, holding the possibility that our cosmos carries the traits of a parent we can never meet. And so the spinning of galaxies becomes more than a mechanical motion. It becomes a whisper of ancestry, a reminder that our universe may have been shaped by forces older than time as we know it. In the stillness of night, when you imagine the galaxies drifting in their graceful arcs, consider the possibility that they are not spinning aimlessly. Perhaps they are moving in harmony with a deeper rhythm, inherited from an event we cannot witness, yet feel in the mathematics of the cosmos. And if we listen closely, if we let our thoughts sink into that ancient quiet, we might sense that the universe is not chaotic at all, but gently organized by a history beyond our horizon. Whether this is truth or only a beautiful hypothesis, it reminds us of our place in something vast, mysterious, and profoundly interconnected. We drift inside a cosmos that may itself be drifting inside another, and another beyond that. And as our galaxies turn in their shared direction, we are left with a final, lingering, human question. If our universe truly carries the spin of a parent black hole, then what ancient story is written in the motion of the stars? And how far back does that lineage of light really go? There are nights when the universe feels closer than our own breath. Nights when the stars seem to lean in and whisper about origins we barely dare to imagine. In such moments, a question rises gently, like a tide against the shore of the mind. A question as old as curiosity itself. Could every black hole be the birth cry of a new universe? Some physicists have said yes, in voices steady with wonder. Lee Smolin once offered a thought that still echoes in the quiet corners of cosmology. Perhaps universes evolve. Perhaps only those able to create black holes survive. His idea was not just a theory but a story of cosmic inheritance, a tale in which universes reproduce through collapse, shaping new realms through gravity's final sigh. When matter falls into a black hole, when it crosses the event horizon and becomes forever unreachable, something extraordinary may be happening on the other side. Not destruction, but transformation. Some theories suggest that instead of a singularity of infinite density, a core of immense compression may rebound. A cosmic heartbeat called a big bounce, where space and time unfold outward as a new universe awakening in the dark. Stephen Hawking once said that black holes are not the eternal prisons they were once believed to be. And that idea lingers like stardust in the mind. If black holes are not prisons, could they be wombs? The thought is both terrifying and beautiful, a reminder that endings and beginnings may share the same door. As this idea expands, it leads naturally to the deeper thread of cosmic reproduction. The notion that the laws of physics may shape which universes survive and which fade into silence. If universes with stable physical constants are the ones capable of forming stars and black holes, then perhaps the very structure of our cosmos is the result of an ancient lineage, selected not by biology but by balance. Michio Kaku once remarked that the universe is fine-tuned to an astonishing degree. And in this context, those words feel like a key clicking into place. If a universe's constants allow black holes to form easily, that universe creates more offspring, more experiments in existence, more chances for consciousness to bloom and wonder to rise again. The transition is gentle here, almost invisible, as the conversation turns to stability, because stability is not just survival. It is the capacity to endure long enough to seed futures we cannot see. Universes with too strong a gravitational pull collapse before light can ever breathe. Universes with too weak a pull drift into sterile emptiness. But a universe balanced just right, with forces that cradle matter rather than crush it, becomes a universe rich in stars, rich in black holes, and therefore rich in new beginnings. In this view, our cosmos is not random. It is the descendant of favorable conditions, the child of universes before it, carrying the inherited harmony of forces that allow galaxies to whirl and minds to dream. It is here that entropy slips into the story like a quiet visitor, unnoticed at first, yet essential to everything. Entropy is the measure of disorder, the count of arrangements possible, the whisper of information hidden in complexity. And black holes are the most entropic objects ever discovered, their horizons storing information in a density that defies comprehension. Jacob Bekenstein once said that black hole entropy is proportional to the area of the event horizon, a sentence of astonishing simplicity that forever changed how we think about information. Stephen Hawking extended the idea and revealed that black holes radiate, that they leak information in the faintest glow, tying thermodynamics to gravity in a way no one expected. And so we arrive at another quiet revelation. If black holes carry enormous entropy, they carry enormous information. And if they give birth to universes, then perhaps that information is not lost. Perhaps it becomes the blueprint for a new cosmos. This thought drifts softly through the mind like a feather caught in a solar wind. What if the information stored in a black hole's horizon becomes the seed of physical laws in the universe within it? What if our own constants are inherited from the entropy of a parent universe long vanished? There is something soothing in that possibility. The idea that nothing is wasted, that even collapse becomes creation. That information woven into a dying star may become the chemistry of new worlds. And as this idea flows onward, it meets yet another question that rises like dawn behind distant mountains. Why does the entropy of black holes match the amount of information needed to describe our universe? Why does the mathematics align so elegantly? Leonard Susskind once said, "The inside of a black hole is a hologram of the outside." And those words glow with significance here. If the holographic principle is true, then the boundary of a black hole may store the information of the universe inside it. Not metaphorically, but literally. This symmetry is not just beautiful, it is suggestive. It murmurs that our universe might be written on a boundary we cannot see, a kind of cosmic skin that remembers everything. And if a black hole encodes information in this way, then a universe born from such a structure may inherit a natural order, a quiet continuity, an echo of the equations that shaped the world before it. The thought unfolds like a soft blossom in darkness, suggesting that entropy is not merely disorder, but possibility, a vast library of potential universes waiting to emerge. In the silence between these ideas, we sense something else, something more tender, more human, the realization that we ourselves are part of this chain, that consciousness may be one of the rare flowers blooming in a universe finely tuned through countless generations. Our atoms were born in stars. Our stars were born in collapsing clouds. Those clouds arose from the expanding fabric of space, and that fabric perhaps unfolded from the collapse of another world. In this sense, we are not merely observers of the universe. We are participants in its long, unfolding story, part of a river that began before time, flowing gently toward futures not yet imagined. And as the mind drifts through this cosmic chain of parent and child, black hole and universe, entropy and information, a final question glows quietly like an ember in the dark. If every black hole can give birth to a universe, then how many universes lie beyond our understanding? And what ancient story are we unknowingly continuing? When we speak of the early universe, we often imagine a silent ocean of darkness, a place where time itself feels as thin as breath. Yet beneath that quiet surface, hidden inside the mathematics of Einstein and the visionaries who came after him, lies a possibility so delicate and profound that it could reshape our understanding of existence. It is the idea that space-time does not simply bend or stretch, but that it can twist, coil, and carry within it a subtle torque known as torsion. In the Einstein-Cartan theory, this twisting is not an afterthought. It is a natural result of matter possessing spin. Every particle in the universe holds a tiny rotation in its identity, and that microscopic spin may echo outward into the grand structure of space-time itself. Some physicists describe this torsion as a kind of whispering motion within the cosmic fabric, a faint spiraling that becomes noticeable only under the most extreme pressures the universe can offer. And as serene as it sounds, this twist could be the very force that saves the cosmos from tearing itself apart at its most violent moments. The famous physicist Dennis Sciama once remarked that spin is nature's way of telling us that nothing ever sits perfectly still. And within the Einstein-Cartan framework, spin refuses to remain confined inside particles. It imprints itself onto the curvature of space-time like a signature on ancient stone. Imagine the universe not at its gentle midlife but at its beginning, when everything was squeezed into scales smaller than imagination, where densities, climbed so high that gravity alone could not describe the story unfolding. In traditional general relativity, this crushing leads to a singularity, a point of infinite density where the laws of physics burn away like paper touching flame. But torsion gently disrupts this path, introducing a repulsive pressure that rises not from energy or matter as we normally think of them, but from the innate spin locked inside every building block of existence. That spin presses outward when densities climb toward the impossible, resisting the collapse into an infinite point. As theoretical physicist Nikodem Popławski famously said, torsion is gravity's hidden strength, rising only when the universe is under absolute duress. In this view, the universe never actually reached a singularity, never broke the laws of physics, never became a mathematical impossibility. Instead, when matter compressed to unimaginable densities, torsion created a recoil, a bounce, a turning point, a cosmic heartbeat where contraction became expansion. Rather than beginning from nothing, the Big Bang might have been that rebound, the outward rush that followed nature's refusal to collapse further. The idea is gentle yet audacious, suggesting that our universe was born from the ashes of another, not as an explosion, but as a release. The Einstein-Cartan theory whispers of a cyclical cosmos, where every universe might arise from the interior of a black hole in a larger parent universe. Under this perspective, black holes cease to be mere cosmic traps, and instead become fertile wombs of creation. The gravitational collapse that we observe becomes only the outward face of a deeper transformation, while inside, torsion prevents true collapse, triggering a renewal that becomes a newborn cosmos. This is why Popławski once said in an interview, "Inside every black hole could be a new universe, expanding beyond the horizon of its parent." It is a poetic thought, yet grounded in careful mathematics. If this is true, then the Big Bang was not a beginning, but a transition. And that transition carries emotional weight, because it reframes the universe as something continuous, regenerative. A place where endings fold into beginnings, the way waves fold into one another at the shore. The torsion born from spin becomes not just a technical correction to general relativity, but a symbol of resilience, a cosmic refusal to surrender to infinite compression. Space-time with torsion is not smooth, but textured, like cloth woven by unseen hands. Each thread carries the tiny rotations of particles, and together they create a fabric capable of withstanding pressures so fierce that they defy comprehension. Where Einstein's elegant geometry once predicted a breakdown, Cartan's addition of spin restores balance, giving gravity a hidden counterpart that steps forward only in moments of crisis. It is as if the universe holds a secret reserve of strength, a calm buried beneath the turbulence. And if the universe experienced such a bounce, what does it say about our place within it? Perhaps it suggests that creation is not a solitary miracle, but a repeating rhythm, a breath drawn and released across unimaginable spans of time. Perhaps it means that the darkness we fear, the collapse into the unknown, is only half of the story, and that renewal waits quietly within the very forces we think of as destructive. Some cosmologists argue that traces of this bounce could still echo through the microwave background. Faint asymmetries, slight directional patterns, the small fingerprints of a universe that once contracted before it expanded. Others point out that we may never know for certain, because the bounce would veil its own origins. Yet the possibility is enough to reshape our imagination, inviting us to see the cosmos not as a single arrow of time, but as a grand cycle. And there is something deeply peaceful in that idea, something that fits into the quiet spaces of human longing. The thought that our universe survived its own collapse, that it endured pressure beyond limits, and blossomed outward instead of breaking, gives the Big Bang a softness, a gentleness. It feels less like a violent birth and more like the first inhale after a long silence. Perhaps this is why so many physicists have spoken of torsion with a kind of poetic awe, even while grounding their work in rigorous equations. As the cosmologist George Ellis once said, the universe is under no obligation to be simple, only to be consistent. And torsion offers that consistency at the edge of physical law, repairing the places where standard relativity would otherwise tear. In the end, the story of torsion and the Einstein-Cartan theory is not just about equations, but about perspective. It asks us to imagine a universe that refuses to destroy itself completely, a universe that carries resilience in every particle, a universe that rebuilds rather than collapses. The idea of a big bounce, with matter compressed to a limit before rebounding into expansion, becomes not only a scientific proposition, but a metaphor for cycles of existence that echo across all scales. And as we drift through these thoughts, floating gently on the notion of a cosmos that twists and breathes and endures, we are left with a question that lingers softly in the dark. If the universe itself can rebound from absolute collapse, what else in existence is capable of beginning again, drifting through the quiet breath of the cosmos? There are nights when science feels less like a discipline and more like a soft lantern carried through an ancient forest. The deeper we look, the more the universe answers with a whisper rather than a declaration. And sometimes, in that whisper, we notice a direction in the silence itself, a subtle lean, a preferred axis threading through the deep fabric of space-time. Scientists call this possibility cosmic anisotropy, a gentle violation of the idea we've carried for a century, that the universe, when seen from far enough away, must appear the same in every direction. This belief is the backbone of modern cosmology, the quiet assumption behind every model and every simulation. But then came the strange alignments in the cosmic microwave background, the surprising patterns in galaxy rotation, the mysterious clustering of quasars across billions of light-years. As Nobel laureate Steven Weinberg once warned, the universe is an old adversary of certainty. If there truly is a special direction, it means the cosmos is not the smooth, uniform sea we imagined, but a vast ocean in which currents flow stronger in one path than another. It means something in our earliest moments, perhaps even before the Big Bang as we describe it, nudged spacetime in a particular orientation. And as the universe expanded, like a breath released from unimaginable density, that orientation remained, a fossil of creation's first motion. This possibility alone would be enough to shake the pillars of cosmology. Yet it arrives hand in hand with another puzzle quietly illuminated by the James Webb Space Telescope. A puzzle of galaxies, too large, too bright, too mature to belong to the childhood of the universe. They glow at a time when the cosmos was supposed to be barely capable of lighting its first candles. Yet they burn like entire cities already built. As one astronomer put it, "We expected newborn stars. But Webb is showing us cities when there should barely be villages." According to the Standard Model, the early universe should have hosted small, fragile proto-galaxies, clumps of hydrogen still figuring out how to ignite their first suns. But JWST found giants where infants should be. Sprawling clusters with chemical signatures implying multiple generations of stars had lived and died. This should be impossible, or at least improbable to a degree that presses the boundaries of the model itself. If these galaxies are real, then our timeline of cosmic evolution is not just incomplete, it is quietly incorrect. As astrophysicist Priyam Vada Natarajan noted, Webb is showing us that the universe grew up faster than any of us expected. But why would such massive structures appear so early, as if formed under conditions more extreme or more organized than our equations allow? Why would matter gather with such urgency, such orchestration, as though gravity itself were guided by a hidden symmetry? This is where the thread of cosmic anisotropy weaves into a larger tapestry. A tapestry that some thinkers believe might point toward an even deeper origin story. If space-time has a preferred direction, then the Big Bang might not have been perfectly symmetrical, might not have erupted as a uniform expansion. Instead, it may have carried the imprint of rotation, of torsion, of a spinning seed from which our universe emerged. And this idea brings us gently to one of the boldest interpretations in modern cosmology. A whisper that has grown louder in recent years, that the universe may have been born inside a black hole. In extended versions of general relativity, especially those involving Einstein-Cartan theory, the collapse of matter in a black hole does not end in a singularity, but in a bounce. Torsion, the twist created by the intrinsic spin of particles, generates a repulsive force at extremely high densities. Instead of crushing matter into an infinitesimal point, the core rebounds, birthing a new expanding region of space-time on the other side. Some call this region a baby universe, others a cosmic branch. But the implication is the same: every black hole could be the doorway to another universe. If our universe was born from such a bounce, then the rotation and anisotropy detected today may be nothing more than the inherited spin of the parent universe. The preferred direction in the cosmic background would then be a scar, a memory, a leftover momentum from a collapse that happened beyond our horizon. As physicist Nikodem Popovsky famously said, if our universe is inside a black hole, then the rotation of that black hole is written into the sky itself. Such a scenario also offers a quiet solution to the early giant galaxies. For a universe born from a highly compressed, rotating state would expand with regions of uneven density, allowing structure to form far earlier than standard cosmology predicts. Gravity would not work uniformly, but along currents, filaments, and the echoes of rotational flow. Matter would clump more quickly. Stars would ignite sooner. Galaxies would bloom where turbulence funneled mass into early knots. The universe would not be a calm, smooth childhood, but a restless newborn shaped by the momentum of its birth. In this light, cosmic anisotropy is not an oba, error, not noise, but the faint heartbeat of a deeper story. A story in which our universe is not the only universe, not even the first, but one branch in an endless family tree growing from the soil of collapsed stars in realities beyond our own. The early colossal galaxies become less a mystery and more a signature of an energetic beginning. A beginning shaped by forces we normally encounter only at the horizons of black holes. And as we drift through these ideas, letting them settle like quiet snow on the surface of the mind, it becomes clear that the more the universe reveals, the softer our certainty becomes. Cosmology is not a monument, but a river. And rivers do not stay still. They shift. They carve. They wander toward truths we can feel long before we can measure. Perhaps the universe has a preferred direction. Perhaps galaxies grew too fast. Perhaps we are living inside a cosmic chamber born from a collapse we will never see. Or perhaps, as Carl Sagan once said, somewhere, something incredible is waiting to be known. And in that waiting, in that gentle open space between certainty and wonder, we find ourselves drifting, listening, and learning to love the universe not for what it confirms, but for what it dares us to imagine. Floating through the quiet tide of the cosmos, there comes a moment when science pauses, inhales, and becomes something softer than certainty, something closer to a whisper in the dark. And in that stillness we turn toward a simple but unsettling question: what if some of our measurements are wrong? Not wrong by carelessness, but wrong in the way ancient sailors misjudged the horizon, because the ocean itself curved beneath them in ways they hadn't yet learned to see. Astronomers have long assumed that the Milky Way spins at a particular speed, a steady swirl of stars and dust wrapped around a hidden center. But recent studies suggest our galaxy's rotation might be slower than we believed, or perhaps faster, or perhaps simply not uniform at all. If that is true, then many of the cosmic anomalies we struggle to explain might soften, bending into harmony with a universe that only ever seemed discordant because we were tapping our foot to the wrong rhythm. The astrophysicist Janna Levin once said, "When we listen to the universe, we must be careful not to mistake our own heartbeat for its music." And maybe that is what has happened here. A misheard tempo, a mismeasured spin, a galaxy whose vast turning has been interpreted through instruments not yet capable of feeling the pulse beneath the noise. When the Milky Way's rotation is uncertain, the distances to ancient galaxies become uncertain. The inferred brightness of early cosmic structures becomes uncertain, and the dramatic impossibilities seen by JWST begin to blur around the edges. Some of those impossibilities, like galaxies too massive to exist so soon after the Big Bang, may no longer be paradoxes at all. Instead, they might simply be echoes of our own misunderstanding, shadows cast by assumptions dressed as truth. But even if measurement errors could soften one mystery, the universe still leans forward with a mischievous smile, offering more questions than answers. Theoretical physicist Leonard Susskind reminds us, the universe is under no obligation to behave in a way that fits our mathematics. And so we stand before a sky that sometimes appears lopsided, where galaxy rotations show strange preferences, where early structures defy the tempo of formation, where nothing is arranged as neatly as textbooks once promised. Could this all simply be our imperfect measurements? Or does the strangeness run deeper, into the bones of space-time itself? As JWST peers farther than any instrument before it, it is not only revealing what is out there, it is revealing what we failed to understand about ourselves. Every faint red glow from a young galaxy, every stretched photon that has traveled across 13 billion years, carries with it a reminder that knowledge is not a destination. It is a pilgrimage. And the path is uneven, filled with detours, lit by lanterns that burn only briefly before darkness returns. Yet, in that darkness, beauty thrives. Because uncertainty is not a flaw of science. It is its heartbeat. Carl Sagan once wrote, "Somewhere, something incredible is waiting to be known." And perhaps the greatest act of cosmic humility is acknowledging that the something incredible may require us to rewrite even the measurements we once trusted most. So yes, it is possible that some of our measurements are off, even ones as fundamental as the spin of our own galaxy. And yes, correcting them could soothe many of the anomalies we wrestle with, smoothing the edges of crisis into gentle curiosity. But even if we corrected every measurement, refined every equation, and recalibrated every telescope, the universe would still lean in, whispering old secrets in new ways. Because the universe is not merely a collection of answers, it is a long breath, a drifting song, a place where mystery does not resist us, but invites us to rest within it. And as the video draws its final breath, we are left with the same soft question that has followed humanity since the first night sky was ever observed. Is the universe stranger than we imagine, or stranger than we can imagine?